the next topic is going to be recursion, and we're going to do merge sort and quick sort and heap sort, and they all take in log n time, right? And so let's talk about uppers and lower bounds, right? We want to say sorting can be done in n log n time. Why? There exists an algorithm that for all inputs, the algorithm gets the right answer. This says sorting, and this is our algorithm. And the running time of our algorithm is within n log n time. Right? Does that make sense? And the lower bound, right? So here, whenever you do first order logic, you move from left to right. Where he says, right, I have an algorithm, right? And he says, oh, I have an input, right? And then we see that the algorithm works. People with me here? We're proving a lower bound, merge sort, right? So if we prove, so now a lower bound says you can't do it faster because for every algorithm there exists an input in which either the algorithm gives the wrong answer or it takes too much time. Right? Does that make sense? Say it again. The way I know you can't sort faster than whatever is because for every algorithm, there exists an input for which either that algorithm gives the wrong answer or it takes too much time. So, right, the devil comes up with an algorithm that he claims works, and then our goal is to come up with an input in which either the input, his algorithm gives the wrong answer or his running time is too long. People kind of understand the game at least? I want you to get the game here. People getting the game? All right. Now, I have a million slides here which are going to prove that sorting, if you're doing comparison sorts, takes n log n time. And we're not going to go into details on it because it'll scare you and we're all getting tired. But let me tell you the top level. The reason I have it in this section is because it's basically, it's a search algorithm, which with loop invariant, right? The devil's given me an algorithm, and I have to find an input on which it either his algorithm gives the wrong answer, or it runs too long. And so it's a search algorithm, right? I'm looking for that input, right? And so I'm going to have a loop invariant which narrows the search space. I have a search space. We flip along here first. So here I have a search space of all possible inputs in which I might give him. And I keep narrowing down the search space. And as I narrow down the search space, I eventually find an input which I'm going to give him, which is going to give the wrong answer or run too long. All right? People kind of get what we're doing? Don't worry about it. It won't be on the test. You can read this if you want to, but you probably won't. Yeah?
The proving stuff will not be on the, like this kind of proving stuff not on the test.
I told you what's on the test. I told you exactly what's on the test. And whether you call that proving or not, you definitely have to prove that you maintain the loop invariant. You have to say, I'm at the top of the loop invariant's true with the old values. You know, I do the code, which gives me the relationship between the old values and the new values. The X condition is not true. Then you have to prove, yes, the word proves there. You have to prove that the loop invariant is true again, right? Well, this case is actually the same, right? The loop invariant is I have a set of inputs, which one of these inputs is going to mess up the algorithm for the first t time steps, and I maintain the loop invariant. Right? So this one, I just told you, if I went through it this fast, I guarantee it's not on the test. So don't panic. Any other questions?
Before you were saying the devil was giving you an algorithm that he says works.
Right.
But if it says for every algorithm, couldn't he just give you a new one that fixes your problem?
Yeah, that's the whole first order logic game. That if I want to prove that for every x there exists a y, I like to think about it as the game as the adversary gives me an x. And he's the devil, so he's going to give me the worst x. And then I just have to come up with a y which defeats them.
Is he stuck with his x type?
Yeah, so we do, in fact, the way we would prove it is we say let x be arbitrary, all right? And suppose I want to prove for every x there exists a y such that y is bigger than x, right? So let x be arbitrary, let y be x plus 1. Look at I win.
So x is just going to be x.
Yeah. All right, any questions about any of this? And that is it for iterative algorithms.